Chapter 13.2 Comparing the variances of two populations. Back in Chapter 10, we learned about hypothesis tests that compare two population mean or two population proportion. One of the t-tests made the assumption that the two population variances were equal. The ANOVA procedure that was covered in Chapter 11 also assumed the two population variances were equal. In this final section of chapter, we will examine a technique to validate this variances assumption while covering both a one-tail case and a two-tail case. As with the single population variances test already discussed, this technique requires that both populations be normally distributed. Testing the variances of two populations, one-tail test. We will use the following example to demonstrate a one-tail test hypothesis that compare two population variances. Suppose Ron owns a Taco Bell restaurant that has a single drive-through window. Ron would like to reduce the variability of the service time that customers who use the drive-through experience. To accomplish this, he would like to test a new system that outsources the drive-through order to a third-party call center. Customer placing order in the drive-through would be actually talking to a centralized call center that would transfer the order information directly to the restaurant. This would free up employees in the Taco Bell restaurant who normally take the orders. The data in table 13.4 show the service time in seconds for customers using the on-site and outsourced system. This data can also be found in the Excel file tacobell.xlsx. Using this data and alpha equal to 0.05, Ron would like to perform a hypothesis test to determine if the standard deviation of the service time for the outsourced system is less than that of the on-site system. Step 1. Calculate the variance for each sample. We can use either equation 13.2 or Excel function var.s to provide the variance for each sample. For this example, let's use Excel, which gives us the following. S2 is equal to 2.184 and the next S2 is equal to 744.42. Step 2. Identify the null and alternative hypothesis. When comparing two population variances, always assign the larger sample variance to population 1 and the smaller sample variance to population 2. Therefore, population 1 is on-site system and population 2 is outsourced system. Ron would like to see if the outsourced system time have a lower variance than the on-site system time. The hypothesis statement would then be as follows. Null hypothesis, sigma square 1 less than or equal to sigma square 2. Alternative hypothesis, sigma square 1 is greater than sigma square 2, or outsourced system has lower variance than the on-site system. Step 3. Set a value for the significant level alpha. Ron set alpha equal to 0.05 for this hypothesis test. Step 4. Calculate the F-test statistic. The test statistic for a two-sample variance test, F, is shown in equation 13.3, where F is the test statistic, S square 1 is the sample variance for population 1, S square 2 is the sample variant for population 2. Plugging our sample variances into equation 13.3 result in the following. F1 is equal to S1 squared divided by X2 squared equal to 2.184.93 divided by 744.42 equal to 2.935. Because population 1 will always have the larger sample variant, the test statistic from equation 13.3 will always be greater than 1. Step 5. Determine the critical value, or F alpha. The test statistic shown in equation 13.3 follows the F distribution, which was first introduced in chapter 11. Recall that this distribution is skewed to the right and has the following degrees of freedom. D1 is equal to N1 minus 1, D2 is equal to N2 minus 1, where N1 and N2 are the sample size for population 1 and 2, respectively. Recall that there were 12 observations for the on-site system and 14 observations for the outsourced system. So, for our Taco Bell example, we have the following degrees of freedom. D1 equal to N1 minus 1 equal to 12 minus 1 equal to 11. D2 is N2 minus 1 equal to 14 minus 1 equal to 13. Therefore, the critical value, or F alpha, can be found in table 6 in Appendix A. An excerpt from this table is shown in table 13.5. Select the portion of table 6 in Appendix A labeled area in the right tail of distribution equal to 0.05, because we set alpha equal to 0.05 for this hypothesis test. Go to D1 equal to 15 column and D2 equal to 13 row. We will find alpha equal to, so the F alpha is equal to F 0.05 is equal to 2.635. This value is highlighted in table 13.5. We can also obtain the critical F-score for our two population variants using Excel f.inv.rt function, which has the following characteristic. f.inv.rt inside parentheses alpha d1, d2 equal to f.inv.rt inside parentheses 0.05, 11, 13 equal to 2.635. Step 6. Compare the test statistic fx with the critical value f alpha. Figure 13.4 graphically illustrates the test statistic and the rejection region for the Taco Bell example. Be sure to always set up the hypothesis statement for a right tail test as the figures show. In other words, assign alternative hypothesis the greater than sign as we did in this example. That way, the rejection region will always be in the right tail of the F distribution. Because F equal to 2.935 is more than F alpha 2.635, we reject the null hypothesis according to figure 13.4. Step 7. State your conclusion. By rejecting the null hypothesis, we have evidence that the variance for population 2 is less than the variance for population 1. Ron can conclude that the surface time for the outsourced system has less variability than the surface time for the on-site system. A two-population variant test has the same normal distribution requirement as a one-population variant test. Specifically, both populations being compared must be normally distributed to achieve reliable results. Testing the variances of two populations, two-tail test. The last thing we will do in this chapter is conduct a two-tail test hypothesis to compare two population variances. We use this test only to investigate whether a difference exists between the two variances rather than to test if one variant is greater than the other. To demonstrate, we'll use the following example. In an effort to control costs, healthcare insurance companies pay close attention to the length of the hospital stay of their customer. Suppose the healthcare insurer Blue Cross Blue Shield or BCBS is interested in studying the difference in the variant in the number of days patients stay at two different hospitals for a specific procedure. A significant difference in the variant and in the variation of stay at the two hospitals might be something BCBS would want to investigate. Data on the stay of 20 randomly selected patients hospitalized at Christiana Hospital and 20 randomly selected patients hospitalized at Bay Health Hospital were collected for the same procedure. This information, along with the standard deviation index for each of the two samples, is shown in Table 13.6. Using this data and alpha equal to 0.05, BCBS would like to perform a hypothesis test to determine if the standard deviation for the hospital stays differ between Christiana and Bay Health for this procedure. Step 1. Calculate the variance for each sample. Because we have the standard deviation in Table 13.6, the sample variance are a straightforward calculation. S square for Christiana is equal to 0.92 square equal to 0.8464. S square for Bay Health equal to 0.7271 square equal to 0.5041. Step 2. Identify the null and alternative hypothesis. Once again, we assign the larger sample variant to population 1 and the smaller to population 2. Population 1 is Christiana, population 2 is Bay Health. Because BCBS is interested only in examining a difference in population variances, we have the following two-tail test. Null hypothesis, sigma square 1 equal to sigma square 2. Alternative hypothesis, sigma square 1 not equal to sigma square 2, or population variances are different. Step 3. Set a value for the significant level alpha. BCBS set alpha equal to 0.05 for this hypothesis test. Step 4. Calculate the F-test statistic. Plugging our sample variances into equation 13.3 result in the following. F equal to S square 1 divided by S square of 2 equal to 0.8464 divided by 0.5041 equal to 1.679. Step 5. Determine the critical value F alpha. For our BCBS example, D1 is equal to N1 minus 1 is equal to 20 minus 1 is 19. D2 is equal to N2 minus 1 is equal to 20 minus 1 is 19. Because we have a two-tail test, the area that corresponds to alpha equal to 0.05 is split evenly. So alpha divided by 2 is equal to 0.025 between two tails in the distribution. This means that the area in the right tail of the distribution is 0.25. Select the portion of the table 6 and Appendix A labeled area in the right tail of distribution equal to 0.025. For this hypothesis test, go to the D1 equal to 19 column and D2 equal to 19 row to find F alpha divided by 2 equal to F dot 0.025 equal to 2.526. We can also obtain the critical F score for our two population variance tests using Excel f.inv.rt function as follows. f.inv.rt inside parentheses 0.025, 19, is equal to 2.526. Step 6. Compare the test statistic fx with the critical value f alpha. Figure 13.6 graphically illustrates the test statistic and the rejection region for the BCPS example. Even though this is a two-tailed test, we consider only the rejection region on the right side of the distribution. This is because when comparing two population variances, we always assign the sample with the higher variance to the numerator of the test statistic calculation shown in equation 13.3. Doing so ensures that the test statistic, or F, will always be greater than 1. Because fx equal to 1.679 and this is less than f alpha divided by 2 equal to 2.526, we fail to reject the null hypothesis. Step 7. State your conclusion. By failing to reject the null hypothesis, we do not have the evidence that the population variances are different for the two hospitals. We are not, however, saying that the variances for patients stay between the two hospitals are equal. That would be accepting the null hypothesis, which is a very bad thing to do. However, from a business perspective, there does not appear to be any reason to investigate the length of stay at these two hospitals further. Thank you.